have 95% of your data contained. I'm going back as soon as I switch the microphone. Yeah. Okay. Okay, so you have here okay, once again, so 50% of all the data points are above this point up here, and 50% are lower. The middle part of the data, bell-shaped curve, you cut out 50% of the middle, that's here on the thick bar. So it's called, this is the box. So this inner part of this violin plot is called a box and whisker plot. So it's a box which contains 50%, and the whiskers extend to 95%. So 95 of your 100 data points are contained within these two whiskers. Yes?
What's the benefit of this plot?
Well, it shows you the distribution. Not only does it show you the distribution with the box and the whiskers, it also shows you, and this is where the violin comes into play, it shows you the actual frequency polygon of your distribution. So this is a bimodal plot, has basically two modes. So it goes down and then you have another occurrence of higher frequency here.
What needs to use a box and whisker plot?
Because you lose this information. The idea is to show as much of your data as possible. So you show the frequency polygon and you show the actual extension of the box and the whiskers. So it's just adding additional information. Yes? A normal distribution would only be a bell curve, which would be like this, right? So then you wouldn't have these two bumps in it.
I'm just confused, like how is it reflecting normal distribution?
Well, it doesn't really. It's a bimodal. It's almost like it's not really a bimodal, but it is a skewed distribution by all means, because that middle score is basically shifted to the lower end. So if you think of a y distribution, of distribution on the y-axis here, it's basically negatively skewed because it shifts to the lower values. Oh no, it's positively skewed because it's rather on the lower end, right? So the tail tells the tail. So basically it points to higher values.
Wait, so it's positively or negatively?
It's then positively skewed.
I thought you said the tail is affected. Yeah.
Now the tail points up here because that's the tail of the normal distribution. If this were a normal distribution, that would be the tail. And it points to higher values. So that's the violin plot. Shows distribution and the actual numerical values of the actual percentiles as well. Yes.
So what is the blue part represent?
The inner part here.
Yeah.
Well, that is essentially the distribution. So this is like when you think of the normal distribution, this is the frequency polygon that we have seen for skewed data and for normal distribution. So this is just, it's shifted, right? So basically look at it, it's like a histogram or a frequency polygon on the for the value on the x-axis, y-axis.
So the big black line is 50% of scores?
This is 50% of values, yeah.
And then just the whole line is?
The whole thing is 95, correct,
And then
yes.
what about the extra 5%?
These are outliers. Usually in the classical box whisker, you would show the outlier as an individual point. So these 5% of points would be shown as actual points.
And is it always just a line, or can it also be like kind of black line?
No, the black line is always a straight line. Yes, yes, yes. Because you got to keep in mind, this is a way how you depict categorically independent variables. So this would be one group. So if you have two violin plots next to each other, you have two levels of a categorical variable on the x-axis. So if you compare now, let's say blood pressure in males and females, that would be males and that would be females right next to it. So it would be two violins. Then you also can compare them against each other. So that's when the x-axis, the independent variable, is a categorical variable. Yeah. Okay, thank you for the reminder. So that was the violin plot. And now let's get to central tendency. All right. So central tendency is essentially a descriptive statistic that reports the center of your data. So this is basically when you think of the normal distribution curve in a perfectly shaped normal distribution, mean, mode, and median should be the very same point. And this is where the normal distribution has its highest peak in a perfectly symmetrically normal distribution. So basically you have with the mean an arithmetic mean as opposed to a geometric mean, but let's not go anywhere close to that. You have a median, which is the middle score, which splits the data in 50%. And then you have the mode, which is the most commonly occurring value, which should be the mean in a normal distribution, and the median. However, problem is that most times you do not have a perfectly normal distribution. And so it's also true with the so-called charity navigator score. So this is the example for today. The charity navigator score is basically an independent institution that reviews the budget and the strategies of nonprofit organizations and basically gives them a score from 0 to 100. So thankfully, most of them are somewhere in the realm of 85 to 95. So this basically, this arrow here indicates the mean. And now how would you calculate this mean? And this is basically to be seen. So we have the actual data. And if you would open the Excel spreadsheet, you can see here all those scores. So I digitalized the scores and I provided them to you so that we can play around a bit with it. So these are the scores from exactly this histogram. So if we were to reproduce the histogram, so we can now go on data, and we're sorting the data according to the values from largest to smallest. So we're basically saying only 1 was 100.
Is it on Canvas?
This is on Canvas, yeah. There's an Excel spreadsheet on module 5. So if we were to select now all of this data, we could now also build a histogram, which we know already how to do. So we're basically selecting all entries. We go here on bar chart and we're selecting here the histogram.
Which document is this?
charitynavigator.xlsx. Module 5. Yeah. So now here we have a histogram. Doesn't look as pretty as the one that Nolan and Heinzen is showing, but it is nevertheless, it is a histogram kind of resembling. You could hypothetically, you could customize these so-called bins. So when you look at the histogram, these are always called bins, these intervals. And you basically, you have here on the y-axis, the frequency of each individual entry within that bin. So this is basically the charity navigator score. Now you can change the title, charity navigator score. And that's a graphical depiction of the distribution curve. So if you were asked to express the central tendency of the graph, the first metric that comes to mind is obviously the mean. And I trust that all of you have done a mean in high school. Basically what the mean is, and that's M. Also keep in mind, whenever you have an actual Latin letter, a letter, rather than a Greek symbol, this is a sample mean. So this is a sample of the population of charity organizations. So this is a sample mean equals, that's an epsilon, that's the sign for sum. It's the sum of all x, where the x basically reflects each individual entry. So that is x1 to x43. So x1, x2, x3. So that's each individual entry. And this means that it's the x, the sum of all x divided by n, and n stands for the sample size. So that's the number of entries. So let's recap. It's basically, it's the sum of all entries divided by the number of entries. So I trust you've all done that, but let's just quickly do that in Excel. So we have here our histogram with the Charity Navigator scores. We are calculating now the mean. The mean is calculated as the sum, SUM, of A2 to A41. Parenthesis closed, that's the sum. So this is the overall sum. To derive from the sum the actual average or mean, you would need to count each entry, which is count, as we know, from A2 to
Yeah, what do you get for the mean?
Yep. So the first one is the sum.
Oh, it's only to find the sum of it.
The sum of A2 to A41 divided by the count from A2 to A41.
Do you mind making the formula a little bit?
Yeah.
Do you mind doing it again? So you can see?
Yep, we can do it again. So once again, so we need the sum X and sample size X. So this is sum SUM A2 to A41. I'm gonna copy this formulas and we'll separate. I'm gonna do this. Let's do this. Make this a little bigger. Is this better legible? Yeah, good. So this is the sum from A2 to A41. Now I want to count the number of entries. Let's count A2 to A41. This is where we're just replacing the sum here with count.
And you do that divided by.
Exactly. And to get to the mean, you calculate the sum divided by 40. That's your mean.
Just write equals
Hmm?
G4.
This is equals G4 divided by G5.
Is there a way to have all in one thing, or do you have to do something?
No. You can do it in one. Yeah. That's the same thing if you do sum.
Well, like sum equal whatever in brackets that you go over and count.
Yeah. So then just to illustrate it, you can do you just can express it as a normal formula in one line, right? You can. Oops. I show the formula right here. No.
That's the mean.
Correct. That's the mean. You can alternatively also make it easier. So this is just to illustrate how to calculate this. So this is the formula as a one-liner.
You do that all in one sentence.
You can do it all in one. Yeah. You can alternatively, and now it's getting easier. Now you can also do average A2 to A41. Then it does this automatically for you.
Oh, so like,
For didactic purposes, because I want you to learn the formula. That's why. This is average A2 to A41. So the reason is I want you to learn how to do this thing step by step, because only then you really understand the underlying dynamic, right? So that's the idea.
What is the like bottom line so that we shouldn't use the.
Not for now, no. Actually, for the homework, and I will explicitly make that point, I want you to calculate everything by hand. That includes the, yeah. Yes, yes, yes. It should be an exercise, right? I know, I know. Well, I can code the same examples within 30 seconds in R, but then we're not learning how to do it, right? So that's the idea. It's like only if you do this step by step, and it looks super simple and like an unnecessary exercise. But if you understand these underlying arithmetics, everything we will learn moving forward just becomes much more intuitive. And that's really what I strongly believe in. So I started programming statistics before I actually sat down and did all the statistics by hand. That's also a reason why I started teaching, because it actually forced me, and I just got so much joy out of figuring all these dynamics out. So there's a lot of value in that. Trust me. Yes.
So central tendency, you're just finding the mean of a histogram?
It's one marker of central tendency. It's mean, median, and mode.
Oh, those are all markers.
All three are markers of central tendency.
So then what exactly is central tendency?
It's a description of it's a descriptive statistics of the center of a distribution.
So
Yep.
you need to know how to find it between mean and mode?
Yes. Yes, yes, yes. So this being said, so we're coming now to the next marker of central tendency, which is the actual median. And so now there's so for the mean, yes, and this comes back to what I said before. If you have an M or an X bar is basically an X with a bar on top, then you're talking about a sample. And then it is labeled as statistics. And
X bar,
X bar is basically X bar.
and that's for me.
That's a mean in a sample.
What do you mean by a sample?
So a sample is, you have a population, but then you pull like 100 people out. That's the sample. Population versus sample. And we will deal with this quite a bit. So for that very reason, it's important that you memorize this table. I'm flagging this as being a quite central table to that chapter. So when you have a sample, you have M or X bar. Nolan and Heinzen use that interchangeably. A little confusing at times, but we'll keep that in mind. It's M or X bar, then it's a sample. And in a sample, a central tendency is a so-called statistic. Whereas in a population, it's called a parameter. And this parameter is indicated with a Greek letter, which is here the letter mu, which is the Greek U. Okay.
Will we be dealing with both
Hmm?
samples? Will we be dealing with both samples?
Yes, you will. Yes, you will. Because we're drawing a sample, and this is actually an exercise that you do in real life too. When you look into comparing the sample to the population, you have a population mean given, you have a sample at hand, you want to compare your sample to the population. This is what we will do with one sample SET test and one sample t-test, which is going to be our segue into hypothesis testing. So, okay, calculate the median. Median divides the scores in 50% greater than that number and 50% lower than that number. Easy, right? So what we need is nothing else but sorting all our scores, which we've done already. You sort it from the highest to the lowest. Then you basically figure out you sort it, yeah. So you have by selecting the entire series, go on data, go on sort.
Where's data? Oh, data.
Yeah, and here you go on sort. And here you have column scores. Make sure you select that my list has headers. And you sort from largest to smallest.
Values.
When would you not select my list as headers if you don't think it is?
If there's no header. As soon as there's a header, you indicate there's a header. Okay, again, you sort by column scores. You sort them based on their values. You sort them from largest to smallest, and you select my list as headers.
What do you like for column? Do you have to change anything in column?
Not at this point. No, you could, but not right now. Well, you could do it if you want to sort that particular aspect according to a second column that you have right next to it.
If you want to sort it to.
According to a different column. Let's say you have a second column next to it and you want to sort it based on that, but you only want to sort that column. So there are rare use cases where you would need that, but for now, this is what we do. Question? No. So now we need to kind of label that through from 1 to 40. So it's 40 entries. So 40 entries obviously create now 2 middle scores, right? So it's a little bit trickier because you have.
You're writing down the numbers.
Yep. So if you have, you have here with 20.
You're writing down the numbers next to it.
Yeah, that's just 1, 2, 3.
What do you do?
You just write 1, 2, 3, and you double click this little. Remember this one?
That,
The little corner, the right lower corner, and you're just completing the series.
oh no, became all three.
Yeah, you need to select 1, 2, 3, and then click it.
Oh, select all of that.
It needs to recognize. It needs to recognize the series that you want to continue. Okay, so we have 40 entries. What's the middle value? What separates? Yeah. Not bad. So you essentially what you're dealing with, you have 2 different values that constitute your middle. So this will separate your 50%, right? So you have here 90.2 and 90.1. So what can the median be? Essentially what you do, you calculate the average between those two. So it's 90.15 is going to be the average.
Just making everything 3.
Oh, sorry.
Like when I drag it down, it's just making everything 3.
Okay, select 1, 2, 3, select all 3,
Yeah.
and then double click the right lower corner.
Yeah.
Then it will recognize it as a series.
The bottom on the bottom right.
Okay, so this is now how we get our median. So this middle score is found by basically finding the middle value. So if there's an uneven number, you have one number that basically separates the upper 50% and the lower 50%. So that's your median. If you have 2 numbers, like in our case, you build the average between both.
How did you know in RT said there was 2 numbers?
Well, because it's 40.
Oh, so you have an even number?
Every time it's an even number, you take the middle 2 values and you divide them by 2. You sum them up, divide them by 2. So you build an average between those 2. So alternatively, so we are having now our median defined. So you can do the median also with the median function. So that's median A2 to A41. And this is your 90.15, right?
Wait, how do you do that?
It's the median function.
You
So
don't
it's,
want to see that.
well, I don't want you to use it right now, but down the road you will use only this function because
So why do you equal median?
yeah, you do equal median A2 to A41.
Oh, I got it.
Yep, very good. Yeah. Alternatively, you can also, if you want to do it properly, you do average of 20, these two, right? So that's 90.15. Same thing. Yeah. A21, A. All right, so this is the median. This is the median. Again, this separates the entire data set into 2 equal parts. So that's 50%. Well, because it's not the same number, right? It's different. Mean and median is different. No, but this is just the average of these 2 numbers. That's how you calculate the median. You take the middle 2 numbers, you calculate an average. So Any questions? Any questions? Are there any questions? No? Good. All right. Okay, so this is 50%. This is now 50% of our data. So now there's also the mode, and the mode is basically the most often occurring value, which essentially is to be evaluated by counting each entry, right? So you line up the scores in ascending order and you find the most frequent scores.
We can't just see like equals. There's no mode, right?
Yeah, no, there's unfortunately no way like that. It's the mode is not really something that is usually calculated. It's a very rare use case, very rare.
You just count from the chart.
You count it from the chart, although actually could.
Why do you do frequency?
Mode, oh wait, mode. A2 to A41. Yeah, 98.2 is the most often. Okay, so there's a function. All right, good. It is not something that it would commonly calculate because it's usually you see it in a histogram, so this is your mode. It's not really a commonly used descriptive statistic. Yes. The 97.9. They're all most often occurring.
Yeah, they're all occurring.
97, 98. Yeah, you're right. It's a good question. Why he would, why actually would choose? My intuitive guess would be it takes the higher value. That's my intuitive guess, that it follows the frequency polygon, and it basically takes the highest value. And this is like, okay, so this is. That's what I assume. Sorry. Excuse me. Can we just one conversation, please?
Then would there be no mode, or would there be like two modes?
Well, it depends. If you have, so in essence, it would be a function. You would describe a function over this data, and this is how Excel derives these values. And I guess it's the peak of that function. So it will model a function through the entire data points, and it will take that peak. I am not 100% sure why it would choose 98.2 over 97.9. It's an excellent question, to be honest. I assume because it's the peak of that function that Excel is fitted through. I'll dig into it, though. I'm interested myself now. But in principle, in its simplest form, it's the most often occurring value. And this is here the point, equally often for both. So it would be both kind of. So essentially, it would be next to each other in the same bin. It would be one mode, right? Because it's only 2 times occurring, so that's not that often. Also, histograms most often show bins. So then the most often occurring value would be that bin. So yeah, but this is a good question. Yes, you were first. You had a question? Yeah? No?
Oh, yeah.
Yeah.
Find the mean, can you just use the average? Instead of doing the whole long formula there?
Not yet. So for the homework, you're being asked to actually calculate by hand. For the first homework, notably. For
You can't use the average for that, even though you got.
not in the first homework. In the first homework, I want to see those calculations, and I want to see the actual formula.
Okay, even though you got the same answer.
Yes, I'm annoying like that. Okay. Yeah. No, there was a question. Sorry. Yep.
Yeah. So the mode is supposed to take the most frequently occurring number, right?
Correct.
So I did the mode as like column A, but it doesn't give you the most frequently occurring number.
It gives you 98.2, right?
No, you need 86.4, and like there's a lot of numbers.
So do you have the same formula as this one? Do you have mode A2 to A41?
Yeah, I figured as you wrote it just to check, and it's not really, so like is mode really on Excel just
You have mode A2 to A41.
yeah,
Did you sort it?
sort it?
Yep.
Yeah.
Okay, we got to look at this after class. I'm not sure I have an answer up my sleeve now. Let's look at this. It shouldn't be. Well,
How come you wrote 50% by the, the mean?
Why it's not identical?
No, you said something about the median and how that's like 50% of the data.
That's the threshold below which you have 50% of the data and above which you have 50% of the data. It's one value. Yes. Other question?
No, I got it.
Oh, okay. Good. Okay, so let's move on. Okay, so we have mean, median, mode. We have discussed these three. Don't worry too much about the modes. In essence, what the mode is being used for, it is used to describe your distribution. And this is usually done to characterize it either as unimodal, and that's the normal distribution, or bimodal, which was basically having two peaks in the distribution, or multimodal. As you can think, there are various reasons why that would happen. For example, here you have a time series of the age distribution of American girls named Violet. So basically you have the number of violets born each year was very high in earlier times, then it kind of got a very unpopular name, and then it had a renaissance after 2014. So this is, for example, where you see a bimodal distribution. It's not the best of all examples, but it is one example. Also in biological data, you see often two modes for different pathophysiological conditions. So somebody has inflammation, more likely high of inflammatory parameters. Somebody doesn't have inflammation, low parameters. So we have two modes. Yes.
How can you know that that's a final, or
That's
how do you know that that graph is a final?
because it has two modes. So it increases twice, right? So you have two peaks, so to say. So that's a multimodal or bimodal distribution. Good. Histogram. Also, this has a bimodal distribution because here you have like a couple of outliers for which I would not donate my money. That came was a 12.5. So since this is an outlier, but it's so much of an outlier that it's almost creating a second mode.
How is it a mode? How is it a mode?
Well, it's not really a mode. It's too low sample size. But imagine you have a handful, and this depicts how well that score actually works that this entity is producing. Because it could be that those that are not good basically create a second mode here, and then you have a mode of the most charities somewhere on the higher end. Bless you. So, but what this essentially wants to show is the power of an outlier. And now it's getting a little tricky, but it's a very important thought experiment. When you have an outlier, think of the calculation of these two markers of central tendency, mode, three, mode, median, and mean. The only one that is arithmetically derived is the arithmetic mean, because you are summing all values up and dividing them by the number of entries. If you have an outlier, this will affect the calculation of your mean. It's unavoidable. So every outlier will affect the calculation of the mean, whereas both median and mode do not change. The median changes to some extent. It will get shifted if you have several outliers, because it characterizes a certain fraction of this data, but it moves much slower. So when you have skewed data, do not calculate a mean, but use a median rather than a mean. If you have outliers, always compare mean and median and make sure that you capture that skewness. Because if you have skewness, mean and median are not going to be identical. They're going to be different. And you will see that because the direction in which the mean is different from the median, this is the direction you have either the skewness or you have the outliers. Arithmetically, it has to be like that. Yes.
Can I clarify something you said that you shouldn't calculate mean when you have skewed data? Can you explain that?
Yes, yeah, because it doesn't give you a reliable estimate of the real mean. It gives you a skewed mean that is affected by those outliers. So a median gives you a more solid marker of that central tendency. Because if you have a normal distribution, but you have a bunch of outliers that basically pull your mean in their direction,
Even if it's
this
not really true to represent the data.
it misrepresents the bulk of the data. So that's why it's always good to calculate mean and median at the same time. If you exclude the mean, the outlier, then you obviously you remove the effect of the outlier. But in scientific methods, and those of you who will do research will see how hard it is to justify that you removed an outlier, because you need a reason to do that. Well, you need a reason.
I think that's dishonest.
Well, it depends. If you clearly stated in your methods that you excluded outliers for a reason that you use to justify that decision, you're fine. In research, really a lot is about transparency. So you just need to say what you do, and you need to have a justification why you do what you do. So yeah, so it's science by its own right to find good reasons to exclude outliers. Yes.
On the last slide, like, that one.
Mhm.
So like, I don't know exactly what you want to know. It's like the outlier and the mean. Like, what do you want us to know?
Well, you want to have an estimate of the mean that is somewhat reliably reflecting. So this just means to illustrate that this is now affecting the mean. Exactly. If you have an outlier like this, for example, you basically will extremely change your mean because it's such a low value, but it's being treated with the same weight as all the other values. That's the real problem.
But isn't that the same as this one? Like,
yeah.
So both of them are unaffecting the rest of the value.
Yeah, the median and the mode less so. The mean is being arithmetically affected.
The mean is being affected, but not the median.
Not in this case, yeah. If you have more outliers, it will still be affected, but less than the mode, for example, because the mode, by definition, is just the most often occurring value. So when it comes to think about which one is best to use, so we have symmetric distributions: mean, skewed, median, and mode is it's rather a rarity to really characterize the mode. So you basically get an idea of the distribution if you want to yes. No, if you want to characterize your distribution, you would use the mode to say unimodal, bimodal, or multimodal. So this is basically the main use. Or when you have nominal data, where you basically want to characterize the occurrence or the frequency. Yes.
So on a test, would you like give us a graph for like a bunch of data and be like, what is the central tendency that based on these rules, she would tell you?
That would be one example. Yes. Yes. For example. Good. So when we're talking now about central tendency, we also have, based on this shape of the normal distribution, we also have a certain variability around that central tendency. And this is now where we're getting in, so this is really where it's getting analytics. So we have now a range, a variance, or a standard deviation. These three markers of variability are characterizing or helping to characterize this distribution curve that you're looking at. The range is the simplest of them all. That basically gives you an idea, again, outliers, because it takes the min and the max. And the range is basically nothing else but the difference between both. So it gives you an idea of the range of data that you're looking at. For our Charity Navigator score, easily calculatable. So you have the min and the max. Here's the max. That's the min because we did sort it. Easy. The calculation of that is basically done as equal sign min A2 to A41. It's as easy as min, and then you have the max is max A2 to A41. And logically, the range is nothing else but the difference between both. So this is the max minus the mean, with 28.5 being the range. It's min A2 to A41. And that's max. And that's max minus min. So that's the range. So yeah, in a second. I just gotta hurry up with it. I'll show you in a second. Then in addition to that, you have the interquartile range. You have the first quartile, that's the 25th percentile. What is a percentile? A percentile, you have basically, if you characterize your entire data set, you have 1% of data less than the first percentile, 2% of data below the second percentile, 3%, and then it goes on. When you're at 25, you have the first quartile. You're quoting the data. So you have the first quartile, that's 25 to 1%. So it's everything smaller than that value. It's one value.
Out of all the sum of the data and divide by 4?
No, no. You do the median for the lower half. So it's basically, so you have 50%, you take the median of the upper 50% and the median of the lower 50% gives it. Exactly. So that's 25th percentile, the median is the 50th percentile, and 25th percentile, 75th percentile is the third quartile, end of the third quartile. As the name implies, you have 4 quartiles. They're equally sized, and it goes from first percentile to the 100th percentile. So now I'm going back. So this is basically easily done in the actual data. So you basically need to do nothing else but, so this is the max, right? Max A2 to A41. Now you have the median. The median was here from here to here. So you basically, what you need to do now is you're calculating the median from your 20 entries, and that's your median. So that's the median from A2 to A21.
Can you repeat what you, why?
Yeah. So you want to split the lower half or the upper half. So that's actually 75th. Sorry, 75th. That's the 75th percent. That is the third quartile, yes, and that demarcates the third quartile from the fourth quartile.
So it's from B2 to 821?
It is from A21 to A2, yeah. That is 3 and 4. So this median is the 75th percentile. And that splits your data into the fourth quartile above that value and the third quartile below that value, but above the median. Yep, that's 75 or Q3, 75th, Q3.
What do you get?
94.3, that's the, this is median.
It's in between 10 and 11.
Correct. Median A2 to A21.
But isn't that?
Yes, that's all the data.
But isn't
That's the highest value, the max.
Oh.
Yes.
How do we find the first quartile, like 20%?
Well, the same principle applies here. You're doing a median of A22 to A41. That's 87 point.
But the 94.3, isn't that the actual median? Because that's from 8 to 821.
No. The mean is calculated differently.
I know it's from 8 to 821. That's half of it. Is that 50%?
Hmm?
When we use like equal median 8 to 821,
Yeah.
isn't that 50%?
Yes, but the mean is different. The mean is calculated different.
Wait, why is it 821?
What do you mean?
Why don't we start with 822 for the second half of the data?
For the second half of the data? Yep. So I will put. Yeah, so make sure to read chapter 4 for the quiz, right? So it's A22 to A41.
But that's the top is from where?
It's A2 to A21.
Why do we choose the 21st number and not the 20th? Between 20 and 21. That makes sense.
That is the median. That's the average between those two. Yep. Yep. Yeah. Oh, it's 20 minutes. First 20 minutes.
Okay, so I get
No. You can just try to sit somewhere in the back. That's fine.
the notes and the slides?
Yes.
Okay.
Sure.
How is 821 25%?
Hmm?
How is 822 41 25%?
Because this is the lower part of the data. That's it. That's
50%? Isn't that like half of it? So it'd be 50%?
no, but the half of 50% is 25, right?
Yeah.
That's 25% then.
I know, like, are we doing the other half of the whole thing?
No, but yeah, it's the half of the half. So the half of the half is 25% lower than that value, and 25 to 50% is the second quarter.
But we're only going up to 21, and we're doing 22 to 41, so that's half of it.
Yes, so it's the median, it's the half. The median constitutes the half of a certain data set.
Yeah.
So if this is the lower half and you calculate the median of the lower half,
But I get what you're saying, but we're not doing the half and the lower half, we're just doing half of it. Like, we're just doing 22 to 41, that's half of
no,
1 to 41.
this is 50%, right?
Yeah.
Everything below that is 50%. If you take the half of this 50%, you get a value that is splitting that in two halves. Only the lower part. Forget the upper part now.
I know, but then shouldn't we do like equal the median from like 23 to like 34, like that half to 25%?
No, why would you do that? No. You gotta. No, it starts with min. It goes from min to 25%. That's the first quartile. It's 25 to 50, which is the median. That's the second quartile, and then 50 to 75. That's the third quartile, and then 75 and above is the fourth quartile. You're getting misled by the violin plot where you have the middle 50%. That's a different way of looking at the data. So the middle 50% is Q3 to Q1. Yeah.
Okay, guys.
All right. No, it's fine.
Do you know what I'm saying?
Yes. No. It's a different way of looking at the data.
Okay. Because that's just the way you have to put it in to get the right answer, even though.
Exactly. All right. Hi.
Do you have time after this class?
Sure.
Our studio?
Sure. No problem.
Thank you so much.
You're welcome. Bye-bye.